So the next speaker is Kostas Bekris from RUTGERS University. He's going to talk about algorithmic foundations of robotics. Kostas is currently at RUTGERS. He moved to RUTGERS from Nevada, so he decided not to gamble anymore and wanted to go to New Jersey. He got his PhD at Rice University. From there he went to Nevada, and then he found himself now in New Brunswick. Thank you.
Great, thank you for the introduction. So I'll be talking about the algorithmic foundations of robotics. So it's a great time to be in robotics. The head of the Toyota Research Institute is describing an era of the heavy explosion of robotics. You have robots underwater, flying robots, humanoid robots, and the reason that we are making this progress is that now robots are mechanically more capable. We now have access to sensors, computational power, and data that we did not have in the past, and they're becoming increasingly affordable and ubiquitous. And all the projections for robotics are getting more and more optimistic. Back in 2014, there was a projection about how much the market would be, and in 2017, they had to update it about double, which is driven primarily from consumer robotics. So it's the prediction that consumer robotics is actually going to become greater. So as we want to apply robots in more and more applications, algorithmic and computational challenges remain at the core of our modern objectives. And I will focus in one of the classical problems. How should a robot move in a safe and efficient manner? So what are some of the challenges that you face when you try to deploy robots in the physical world? Well, robots have many degrees of freedom. If you want to control, for instance, a robotic arm, you have multiple joints. A humanoid robot has even more. The real world is very messy. Right? My office looks something like this. A lot of objects, very difficult to figure out which object is which. Complex geometries. Many of the real robots have complex dynamics. There is sensing uncertainty. The contacts are complex physical processes. And then you may also want to coordinate multiple robots. And I think those of you that may be on the discrete mathematics side, dealing with combinatorics, every time that you hear many robots, many objects, perhaps you also see an opportunity, because this is where combinatorics really matter. So let me give you some examples of what we can do today with robots that actually, I think, aligns very well with some of the traditional problems in computer science. For instance, in logistics applications, rearrangement problems arise very frequently. So in a work that we did with my colleague, Dr. Jijing Yu, we actually mapped this problem of tabletop rearrangement. What if you go with overhand grasps and move objects in the environment to a classical problem in computer science, the feedback vertex set problem, which is hard to approximate. But through this reduction, we're also able to get efficient algorithms for solving this problem in the real world with robots. Another example is robot packing. Packing problems in computer science have been studied for quite some time. But again, we didn't have robots that were able to actually do it in the real world. Today, given progress in machine learning, for instance, in recognizing where objects are located, as well as partially giving up on grasping and using suction grippers, we actually can develop solutions that can achieve packing. So here we show a video from a paper that was nominated for the Best Automation Paper Award in the last ICRA, which is the biggest robotics conference, where we demonstrate the capability to pack multiple objects, different types of objects, potentially multiple layers of objects, which is a very important application for the industry. And here, the packing is for uniform objects, but now you can start working with combinatorial algorithms that reason, how can I put together many complex geometries and save a lot of space? So Amazon, where I'm spending for this year my sabbatical, is, for instance, very interested in reducing the amount of empty space when they ship a package, right? Because this costs. So that's where combinatorial algorithms, again, can help. But let me dive a little bit deeper into this challenge of how actually the robotic arm moves in a safe and efficient manner. And this is a traditional problem known by in foundation computer science as the piano movers problem. How do I move from an initial to a goal configuration, given that there is a geometry in the environment that I want to avoid collisions with, right? What if you're a piano mover and you want to make sure that you're not going to scratch the piano as you're taking it outside the room? So this problem has a long history. Back in the late 70s and the early 80s, it was one of those prototypical problems that was shown to be hard. And not just NP hard, it's actually a p-space hard problem. This did not stop, however, roboticists from actually coming up with useful representations that help people develop algorithms. For instance, Tomás Lozano Pérez said that instead of actually working in the real space, where the robot has some geometry, we should map the problem in an abstract space where the robot is just a point. We already knew, algorithms for solving problems for point systems. You can have a visibility graph in 2D and so on. So perhaps going into representation that the robot is a simple point can help us solve the problem. Unfortunately, in this representation, the obstacle representation becomes very complex. You cannot actually describe the obstacles. This led eventually John Caney to argue that in the context of the configuration space representation, you can actually map the continuous problem into a discrete representation, a graph. So actually you can come up with a roadmap where from any initial location and any goal location, you can actually connect onto that roadmap and then solve a graph path planning problem. The bad news was that coming up with this roadmap, it takes an exponential amount of computation, right? And this kind of establishes the hardness of the problem as well. But at least it gave a useful idea that we can actually use graphs to solve these problems in the continuous space. People in robotics kept coming up with heuristic but effective methods. For instance, Usama Khatib proposed potential functions. What if my robot gets attracted by the goal but feels repulsive forces from the obstacles? Perhaps I can move along the negative gradient of the potential function. Unfortunately, very frequently you may get stuck in local minima of this potential function, and very rarely you can build potential functions that have one global optimum. Jean-Claude Latobe said, well, every time that I'm getting stuck in the local minimum, what can I do? I can do random walk. And then I can exit from the local minimum and then follow the negative gradient again. And this kind of worked for the first time for some really complex systems to get solutions and get people excited about the power of randomization in the context of robot motion planning. So it was the 90s, randomized algorithms were popular in general in robotics. So this ended up into a method that became very popular in robot motion planning, the probabilistic roadmap method. And it was developed simultaneously at Stanford by Lydia Kavraki, as well as Mark Overmars' group at the University of Utrecht. And the idea is simple. We're going to build a graph, but we're not going to come up with the best graph for the environment. We're going to build a graph in a randomized way. We're going to sample robot configurations. Each one of those dots correspond to a certain placement of the robot inside the environment. We're going to call a collision checker, and if the collision checker tells us that in this configuration the robot is in collision, like in these cases, we're going to ignore these configurations, and then we're going to try to connect neighboring configurations of the robot and build a graphical representation where we keep sampling. And we build the graph now in a probabilistic way. Now, this method does not have the completeness guarantees of traditional approaches. Instead, it is probabilistically complete. As the number of samples you are throwing inside the configuration space increases, the probability of finding a solution, if one exists, goes to 1. So we kind of gave up on some of the more stringent guarantees for something that, however, was very practical. It started solving for the first time high-dimensional robot motion planning problems. It didn't solve all the problems, however. For instance, if you have something like car-like systems, you may want to just use these methods to first come up with a geometrically feasible path, and then you need controllers that will try to follow the trajectory that you actually computed with these methods. One issue is that a geometric feasible path cannot always be mapped to a path that is also dynamically feasible. So these motivated methods that would directly generate controls that are feasible for real systems. And this is called kinodynamic planning. One very popular algorithm in the robot motion planning literature is this rapidly exploring random tree method, RRT, by Steve Laval and James Affner. And you see here how it grows in the base case of what if you have a point system in a Euclidean plane. It has this behavior that very quickly it reaches the unexplored part of the space, and then it kind of fills the details. And it is also probabilistically complete. So this progress in the late 90s motivated a lot of other approaches that were, how can we make these methods more efficient, and applications in a wide variety of domains, from bioinformatics to humanoid robots, and so on. Nevertheless, there were some bad news as well in this case, and this is from the PhD comics. The author, Jorge Cham, visited Willow Garage, one of the most advanced startups in robotics in the late 2000s, and he saw the robot, the PR2, moving around. And PR2 was moving around flailing its arms while trying to solve motion planning problems. And the reason that the PR2 was flailing its arms is it was using desampling-based algorithms. It was using RT. What happens with RT is that it is provably suboptimal. And this was not actually shown until 2010 from the work of Emilio Frazzoli and Sertac Karaman at MIT. They showed that RT is probabilistically complete, and they made the connection with percolation theory from graph theory about what are the conditions actually for these methods to converge to optimal solutions. It turns out that in order for these methods to give you good quality paths, you have to build relatively dense graphs. For instance, if you add a new sample, you throw a new sample into this roadmap, every time you have to check whether you can connect it to log n number of neighbors, where n is the current number of vertices on the graph. And you can also actually maintain just a tree of configurations if you know what is your start point for your motion planning query. And you actually keep the best edge to your log n neighbors. And this gives a very nice dynamic programming property of how the tree explores inside the state space. So this motivated myself and my group to look again into how we can come up with efficient methods in this domain, but how now provide these guarantees in terms of path quality. And we have been working on this balance between practical methods with some guarantees. The asymptotic optimality property that is provided by PRM star and RRT star, developed by Karaman and Frazzoli, is something doesn't mean much to practitioner. A practitioner that is using these methods is also interested in what happens after a finite amount of computation. And what we argued in a series of papers was that we can actually also provide some guarantees after a finite amount of computation. And the type of guarantee in this case is that we can say that the paths we compute are probably near optimal. We can give a probability that we are within an epsilon error from the optimal solution. With some technical constraints, we have to be within the homotopic class of the true optimal. Another aspect was how can we come up with really compact representations that have very high quality paths stored on them. The objective of the roadmap idea by John Canny, was that you're going to come up with a very compact representation to represent these continuous problems. Now we're actually generating relatively dense graphs that for many real problems we cannot even store in a computer in order to get high quality solutions. But graph spanners can come to our rescue. Graph spanners are generating subgraphs where the path quality between any two nodes is going to be at most t times the path cost in the original graph. And we actually proposed the roadmap spanners, so roadmaps that have satisfy the spanner property for robot motion planning. And a lot of work has actually been done in this domain after for the introduction of the term roadmap spanner into the community. We can actually generate roadmaps that have a minuscule number of edges relative to the true asymptotically optimal solution with very small sacrifice in terms of path quality guarantees. The other domain we're applying this asymptotic optimality notion is in the context of systems that have complex dynamics. What if you're controlling a system with acceleration? It turns out that the first methods that achieved asymptotic optimality also required the existence of what is known as a steering function. You need to be able to connect to your log n neighbors. You have to find this shortest path in the absence of obstacles. But this means if you are having a system with dynamics that you have to solve the differential equations with boundary conditions, the start and the goal location, which we do not always have access to such a solution. So we did a base principles study to show that it was still possible to achieve asymptotic optimality even when we don't have access to such a steering function. So although RT star was the first approach that was asymptotically optimal and was computationally relatively expensive, and RRT was probably suboptimal but computationally efficient, we generated a solution that actually has a property of RRT. It works for systems with dynamics, but it is asymptotically near optimal. And in order to kind of see in the base case, what if I have just again a point system, how the trees look for these three different methods. So the original RRT will actually converge to a suboptimal path and will not be able to improve the solution. RRT star is actually the best algorithm for this case because we do have a steering function and it has this nice dynamic programming exploring the space. What we proposed, and it is known as SST in the literature, is this sparse tree that actually also is able to converge to high quality solutions, but the only primitive that it is using is sample a random control from a state that I have already reached, and I'm still going to converge to optimal solutions. And the benefit of SST is that it can actually be applied to a wide variety of systems, including a very exciting system from NASA. I received my career award from NASA on this tensegrity robot, which is the combination of these rigid bodies and soft elements, where it is like a self-actuated marionette. You are pulling these 24 cables to change the shape of the robot. And NASA is really interested in it because you can throw it over an uneven terrain and you can perform planetary exploration. So we've actually applied this first in simulation on the tensegrity robot, and we were now able to solve problems first in simulation that were not possible to solve before with traditional path planning approaches, like going over uneven terrain or even being able to go under vertical obstacles. But what does this mean in the context, of the developments in machine learning? Why should we still be interested in these motion planning methods now that we have access to data and perhaps we can just train a neural network to learn these controllers? In parallel to our development and our work on the tensegrity robot, colleagues at Berkeley, which are leading the developments in reinforcement learning for robotics, Sergey Levin and Peter Abil, also built a controller for this tensegrity robot on how it can move forward on a straight line. But their approach required a lot of data, and it's actually quite painful in robotics to collect data in order to train these kind of solutions, and was able to make the robot only move along a straight line. What we were able to show was that if we trained this system first with optimal solutions in simulation from our kinodynamic planner, we could actually do better. This is the solution from the previously reinforcement learning algorithm from Berkeley, that it cannot actually follow arbitrary paths. But we were able to train first in simulation, given high quality paths with our kinodynamic planner, the SST that I mentioned. And then it was possible also by some reasoning about the symmetry of this system with very few examples to actually train a reinforcement learning approach, a neural network now that controls a policy for this tensegrity robot, to actually be able to follow arbitrary paths. And we showed this, that it was actually now working over uneven terrains. And if we can jump here at the 6th minute and 15 seconds, something like that, you will actually see a demonstration on the real system at NASA Ames. So what we did is that we did our, so it's the next slide. So sorry, it's about 6th minute and 15 seconds, if you can jump to that point in time. Okay, so the point was that we actually generated simulations here at RUTGERS with our simulator. We performed some matching between the simulated system and the real system at NASA Ames. And for the first time at NASA Ames, they were able to make the system go upslope, more than 15 degrees upslope. And this was actually for them a great benchmark because they wanted to motivate their mechanical work that they did. And it was the first time that they had a controller that allowed them to solve this problem. So last slide. These are some of previous. I would like to thank our funding agencies and the students that have worked on these projects, and thank you for your attention.